An RLC circuit consists of a 150 ohms resistor, a 21 microfarads capacitor, and a 460 millihenry inductor connected in series with a 120 volt 60 Hz power supply. In the first part of the problem, we need to find the phase angle between the current and the applied voltage. Well, let's write down what the problem gives us. It gives us the resistance, the capacitance, the inductance, the maximum voltage provided by the power supply, and the frequency of 60 Hz. The phase angle can be calculated as the difference between the inductive reactance XL and the capacitive reactance XC divided to the resistance R. So what we need to do is find the inductive reactance and the capacitive reactance. The inductive reactance can be calculated as the angular frequency omega multiplied by the inductance. The angular frequency is related to the frequency by the equation angular frequency equals 2 pi frequency f. So we can calculate the inductive reactance as 2 pi, frequency is 60 Hz, and the inductance is 460 millihenry. Don't forget to convert it to henries, so you will have 0.46 henries. And plug all this into a calculator and you get that the inductive reactance is 173.3 ohms. Similarly, we can calculate the capacitive reactance as 1 over angular frequency omega multiplied by the capacitance C. Again, omega can be written as 2 pi frequency. Frequency is 60 Hz, the capacitance is 21 microfarads. Don't forget to write it as 21 times 10 to minus 6. And using a calculator, we obtain a value of 126.3 ohms for the capacitive reactance. All we have to do now is take the value of XL and XC and replace it in the tangent phi equation. And using a calculator, which you don't forget have to have in radians, you get that the angle phi, the phase angle between the current and the applied voltage, is 0.3 radians. In part B of the problem, we need to determine which reaches its maximum earlier, the current or the voltage. Well, all we have to do is look at the phase angle, and you see that the phase angle is positive. Not only that, but XL has a bigger value than XC, which means that in this case, the voltage leads the current. In part C of the problem, we need to find the maximum voltage between the 2 points of the circuit that include the capacitor in the inductor. The capacitor and the inductor have voltages that are out of phase by 180 degrees. So the phasor for the voltage across the capacitor and the phasor for the voltage across the inductor are parallel and in opposite directions. All we have to do in order to find the voltage across those two elements is add up the phasors of the voltage across the capacitor and the inductor, which means you basically have to subtract them since they are parallel and in opposite direction. So the voltage across the inductor and capacitor together will be the voltage across the inductor minus the voltage across the capacitor. The voltage across each element can be written as the current multiplied by the reactance of that particular element. And as you can see, in order to find the voltage across those two elements, we need to figure out what is the maximum value of the current in the circuit. Well, the maximum value of the current is calculated as the maximum voltage in the circuit divided by the impedance. We need to find the impedance now. Well, impedance is calculated as square root of resistance squared plus the difference between XL and XC squared. We know every single value. We know R, we know XL, we know XC. Plug in the numbers and you get that the impedance is 157.2 ohms. We know now the impedance, we know the maximum voltage, which is 120 volts. So we can go back in the equation for the potential across the inductor and capacitor together, and we will have 120 for the maximum voltage divided by the impedance 157.2 multiplied by XL minus XC, or 173.3 ohms minus 126.3, and we get an answer of 35.87 volts. So this is the maximum voltage that can be collected if you connect a measuring instrument, for example, across the inductor and capacitor together. In part D of the problem, we need to find the average power delivered to the circuit. The average power can be calculated as the RMS value for the current square multiplied by the resistance, or remember, the RMS value is related to the maximum value divided by square root of 2. So we can calculate the average power as the maximum value of the current square divided by 2 multiplied by the resistance. All we have to do is plug in the numbers. Maximum current, I haven't calculated the value of it. I just wrote it as Vmax over the impedance Z. And if you plug in the numbers, you get that the average power is 43.7 watts. In part E of the problem, we need to find the energy delivered to the circuit during one period. Power and energy are related to each other. Power represents nothing else than energy per unit time. Therefore, we can calculate the energy as power multiplied by the time interval. But in this case, the problem says we need to find the energy delivered to the circuit during one period. Well, one period can be calculated as 1 over the frequency. So period and frequency are related to each other. Therefore, I can calculate the energy as power multiplied by 1 over the frequency, and that gives me a value of 0.73 joules. This is the amount of energy delivered to the circuit during every single period.